What if I told you that the universe has a built-in speed limit, and that this limit is not just a rule about motion, but a deep statement about how reality itself works? Right now, as you watch this, light is racing across space at a fixed speed, and nothing, absolutely nothing with mass, has ever been observed to outrun it. Not a spaceship, not a particle, not even the most violent explosions in the cosmos. This is not a technological limitation. It is a fundamental boundary of nature. And when Richard Feynman explored what this limit truly means, the implications were so strange, so counterintuitive, that they continue to challenge how we understand time, space, and cause itself. If this question has ever crossed your mind, leave a comment right now saying what you think sets this limit. And stay with me, because what you are about to hear may permanently change the way you see the universe. Before we go any further, take a moment to subscribe to the channel, leave a like, and share your thoughts in the comments. Your engagement helps keep these ideas alive and reaching curious minds just like yours. The speed of light is often presented as just a number, about 300,000 kilometers per second. But for Feynman, that number was not the interesting part. What fascinated him was the fact that this speed appears everywhere, in electricity, magnetism, optics, and even in the structure of space and time. It is not merely the speed at which light travels, it is the speed at which information travels. It is the speed at which cause and effect are allowed to propagate through the universe. Feynman insisted on something simple, yet radical. If nothing can move faster than this limit, then this limit must be telling us something profound about how nature is built. And the moment you take that idea seriously, everyday intuition begins to break down. Because in daily life, speeds add up. If you walk inside a moving train, your speed relative to the ground is just the sum of your walking speed and the train's speed. But at very high speeds, near this cosmic limit, nature refuses to behave that way. According to Einstein's relativity, which Feynman masterfully explained in his own unique style, as an object accelerates closer and closer to this limit, strange things happen. Time itself begins to slow down for that object. Lengths contract, mass effectively increases. These are not illusions or measurement errors. They are real physical effects, confirmed by experiments again and again. And Feynman loved emphasizing that nature does not care whether these effects feel reasonable to us. Nature simply does what it does. One of Feynman's most powerful insights was to strip away the math and ask a childlike question: why should there be a limit at all? Why does the universe forbid faster motion? His answer was not mystical. It was brutally honest. The limit exists because if it did not, the entire structure of cause and effect would collapse. Events could influence other events before they happened. Signals could arrive before they were sent. The universe would no longer be logically consistent. Feynman explained that the speed of light is woven into space-time itself. Space and time are not separate stages where events happen. They are part of the same fabric, and this fabric has rules. One of those rules is that no influence can propagate faster than this fundamental speed. This is not a rule imposed from outside. It is a property of the fabric itself. To make this feel real, Feynman often turned to thought experiments. Imagine trying to push an object faster and faster. You supply more energy, more force, more effort. But instead of gaining unlimited speed, the energy goes into warping time and space around the object. The universe resists. It is as if reality pushes back, not with friction, but with geometry. And here is where Feynman's honesty shines. He openly admitted that even though we can describe this behavior with equations, our intuition is still catching up. We know what happens. We can predict it precisely, but fully grasping why reality is this way remains one of the deepest challenges in physics. That, for Feynman, was not a weakness of science. It was its beauty. Because the moment you accept that nothing can outrun this limit, you begin to see the universe not as a collection of objects moving through empty space, but as an interconnected system where information, energy, and causality are tightly bound together. And once you see that, the question stops being how fast something can move and becomes something far more unsettling. What would reality even be if this limit did not exist? That question opens a door to consequences that are even stranger, touching time travel, particles that seem to move backward in time, and the deep connection between light and matter. If we push this idea further, the speed limit of the universe stops being just a restriction and starts looking like a kind of organizing principle. Feynman pointed out that many of the strangest phenomena in modern physics only make sense once this limit is treated as absolute. Take, for example, the behavior of particles at the quantum level. Some particles appear to pop in and out of existence, exchanging energy in ways that seem to defy common sense. Yet even in this bizarre microscopic world, no usable information ever travels faster than this fundamental limit. Nature allows strangeness, but it protects causality with ruthless consistency. Feynman loved to emphasize that this limit is not about light itself being special as an object. If tomorrow we discovered a different kind of particle that had no mass, it would also travel at exactly the same speed. The limit is universal. It does not belong to light. Light belongs to it. That single realization flips the usual story upside down. We are not saying that light is incredibly fast. We are saying that reality has a maximum speed, and light simply happens to move at that speed. This perspective leads to an unsettling conclusion. If you were somehow able to ride alongside a beam of light, time for you would stop completely. From your point of view, the entire universe would collapse into a single frozen instant. Feynman was careful here. He explained that this is not something an object with mass can experience. It is a limit that can be approached but never reached. Still, the implication is profound. Time itself is not absolute. It depends on motion, and motion is constrained by this cosmic boundary. Feynman often warned against fooling ourselves into thinking we truly understand this just because we can repeat the words. He insisted that saying time slows down is not an explanation. It is a description. The deeper truth is that time is part of the same structure as space, and that structure is governed by this speed limit. Once you accept that, many apparent paradoxes dissolve, but only if you are willing to abandon everyday intuition. Consider simultaneity. In ordinary life, we assume that if two events happen at the same time for one observer, they happen at the same time for everyone. But near this limit, that assumption fails. Feynman explained that two observers moving relative to each other can disagree about whether events happen simultaneously, and both can be correct. The speed limit forces the universe to give up the idea of universal time. There is no single cosmic clock ticking away in the background. This is not philosophical speculation. It has real consequences. Technologies like particle accelerators rely on these effects every day. Particles live longer when moving close to this limit because time literally passes more slowly for them. Satellites correcting their clocks must account for these effects, or navigation systems would drift and fail. The limit is not abstract. It is woven into the practical functioning of the modern world. Feynman also highlighted something deeply humbling. The universe does not provide reasons in the way humans want reasons. We can ask why there is a speed limit, but at some point physics answers with structure, not purpose. The equations work, the predictions match reality, and beyond that, nature remains silent. For Feynman, learning to live with that silence, without inventing comforting stories, was part of intellectual honesty. Yet this silence is not empty. It invites deeper questions. If the speed limit shapes space and time, then what happens at the boundary where known physics breaks down? What happens near black holes, where space-time itself is stretched to extremes? What happens at the very beginning of the universe, when everything was compressed into unimaginable density? In those regimes, the speed limit still stands, but our understanding starts to fray. Feynman believed that progress comes from standing exactly at that edge, where understanding is incomplete, and refusing to pretend otherwise. The speed limit is one of those edges. It is simple to state, impossible to violate, and endlessly mysterious in its consequences. And as we push closer to it in thought, we begin to encounter ideas that feel almost forbidden. Ideas about particles appearing to move backward in time, and about symmetry between matter and light that challenges our deepest assumptions. Those ideas do not belong to science fiction. They emerge naturally once we follow the logic of this limit all the way to its unsettling conclusions. And that is the path that now unfolds. When physicists followed this logic to its extreme, they encountered something that even Feynman admitted felt almost absurd at first glance. Equations describing particles moving very close to the universal speed limit began to allow solutions where particles appeared to travel backward in time, not metaphorically, literally backward. Instead of rejecting these results outright, Feynman did something characteristic of his mindset. He took the mathematics seriously and asked what it might be trying to say. This is where his interpretation of antimatter emerged. Rather than treating antimatter as an exotic curiosity, Feynman reframed it in a strikingly simple way. An antiparticle could be understood as a normal particle moving backward in time. This was not just a poetic idea. It was a precise mathematical interpretation that made calculations cleaner and predictions clearer. Once again, the speed limit was at the heart of the story. The structure of space-time, constrained by this limit, naturally allowed such interpretations. Feynman was quick to point out that this does not mean we can casually travel into the past or send messages to yesterday. The universe is far more disciplined than that. Even when particles are described as moving backward in time, the overall structure of cause and effect remains intact. The speed limit acts like a gatekeeper, allowing strange internal behaviors while preventing paradoxes from spilling into everyday reality. This balance between freedom and restriction fascinated him. Nature permits elegance and symmetry at the deepest levels, but enforces strict rules on what can be observed and used. You can calculate virtual particles exchanging energy faster than the limit for incredibly short times, but you can never extract information from that process. The universe flirts with impossibility, but never commits to it. Feynman used this to teach a broader lesson about understanding. He argued that many people confuse familiarity with comprehension. We grow used to phrases like, "Nothing can move faster than light," and stop feeling their weight. But if you truly sit with that statement, if you follow it honestly wherever it leads, it dismantles naive ideas about space, time, particles, and even existence itself. He also stressed that this limit does not arise from experimental inconvenience or lack of imagination. It is not something engineers will eventually overcome. It is built into the geometry of reality. Asking how to exceed it is like asking how to draw a triangle with 4 sides. The question itself misunderstands the structure it is trying to challenge, and yet, Feynman never framed this as discouraging. On the contrary, he found joy in it. The fact that reality has deep, non-negotiable rules makes discovery meaningful. If anything were possible, nothing would be interesting. Constraints give shape to curiosity. The speed limit is one of the most powerful constraints we know, and precisely because of that, it unlocks an extraordinary range of phenomena. As physics advanced, researchers began exploring theories where this limit might emerge from even deeper principles, or where space-time itself might be quantized at unimaginably small scales. Even in these speculative ideas, the limit refuses to disappear. It may be reinterpreted, reformulated, or derived from something more fundamental, but it remains, like a shadow that cannot be outrun. Feynman cautioned against expecting final answers. Science, in his view, is not a monument to certainty, but a process of refinement. Each explanation opens new questions. Each boundary reveals another layer of mystery. The speed limit is not the end of inquiry. It is a signpost pointing toward deeper structures we are only beginning to glimpse. And this brings us to the most unsettling implication of all. If this limit defines how reality communicates with itself, then understanding it is not just about motion or energy. It is about the nature of knowledge, observation, and what it even means for something to happen. At that point, physics quietly transforms into a meditation on existence itself, and the final pieces of this puzzle begin to fall into place. At this deepest level, Feynman invited us to confront an idea that feels almost philosophical, yet is grounded entirely in physics. If nothing can move faster than this limit, then knowledge itself is limited. No observer can instantly know what is happening everywhere. Every observation is delayed. Every piece of information arrives late. The universe does not reveal itself all at once. It unfolds in layers, constrained by how fast reality can communicate with itself. This has a startling implication. There is no all-seeing perspective inside the universe, no privileged frame of reference. Every observer carries their own version of time, shaped by motion and constrained by the same unbreakable boundary. Feynman loved this because it stripped away the illusion of cosmic centrality. We are not watching the universe from the outside. We are embedded within it, subject to its rules. From this viewpoint, the speed limit becomes less about speed and more about humility. It tells us that nature does not owe us immediate answers. There will always be horizons beyond which information has not yet arrived. Even the most powerful telescope does not show the universe as it is now, but as it was. We are always looking into the past. The present, in a universal sense, does not exist. Feynman emphasized that this is not a flaw in human perception. It is a feature of reality. The universe is not constructed to be convenient or intuitive. It is constructed to be consistent. And consistency demands limits. Without them, the concept of an event would lose meaning. Without them, cause would no longer precede effect. Without them, science itself would collapse. What makes Feynman's message so enduring is not just the content, but the attitude. He did not ask us to accept these ideas as dogma. He asked us to play with them, to test them, to doubt them honestly. He believed that real understanding comes not from reverence, but from curiosity combined with rigor. The speed limit is not sacred because famous scientists declared it so. It is sacred because every honest experiment points back to it. And yet, Feynman never claimed that this was the final word. He openly admitted that our current theories are incomplete. There may be deeper principles waiting to be discovered, principles that explain why this limit exists, rather than merely describing its consequences. But whatever those principles are, they will not restore common sense. They will likely be even stranger. This is where the emotional core of Feynman's legacy reveals itself. Science, for him, was not about comfort. It was about wonder, the realization that the universe has a maximum speed, that time bends, that particles can be described as moving backward in time, should not make us feel small or confused. It should make us feel lucky to live in a universe that is intelligible at all. Because against all odds, this strange, rule-bound reality allows minds like ours to ask questions about it. It allows equations scribbled on paper to predict events billions of light years away. It allows a simple idea, nothing can move faster than this, to unlock insights into the nature of existence itself. So when you hear that nothing can exceed this limit, do not hear it as a restriction. Hear it as an invitation to rethink motion, time, knowledge, and causality. An invitation to adopt the kind of honest curiosity that Feynman championed, to admit what we do not know, to delight in what we can discover, and to never stop asking questions simply because the answers are strange. In the end, the speed limit of the universe does not shatter our understanding because it is too complex. It shatters it because it is too simple, too absolute, and too deeply woven into everything we thought we understood. And once that realization settles in, the universe never looks quite the same again.